All right, let's dive right in. So, picture this. You're staring at your multimeter screen. You see that little OL pop up, and you instantly assume, well, that component is totally fried, right? It's literally one of the most common traps out there in the field. But misinterpreting that single, simple reading, that can send you down a massive rabbit hole of misdiagnosis. Today, we're going to fix that. Our main goal here is to take those digital meter readouts, specifically those tricky resistance and continuity numbers, and translate them into the actual physical realities happening inside your HVAC or electrical systems. Here is our game plan for today. First, we'll decode multimeter resistance readings. Second, the golden rules of testing. Third, checking loads to see if they're good, open, or shorted. Fourth, testing switches and breakers. And finally, evaluating protection fuses. Decoding multimeter resistance readings. Let's tackle the big one first, OL. Now, depending on your exact meter, it might stand for open line or maybe infinity. But look, when your screen shows OL, it is not just a blank screen waiting for a signal. In the physical world, it means the bridge is completely out for electron flow. It indicates an open circuit, a physically broken wire, or a resistance that is just so incredibly high that absolutely no current can pass through. It's a total roadblock. So think of these as the two absolute extremes of our diagnostic world. On one side, you have 0 ohms. This means maximum flow, a completely closed and unbroken path, or in a bad scenario, a direct short circuit. It's an unrestricted highway. On the exact opposite side, you've got OL, or infinity. 0 flow, a completely broken path, and open circuit. When you're troubleshooting, you're constantly trying to figure out if your path is this wide open highway or a collapsed bridge. But wait, what about everything that happens in between those two extremes? Well, that's where this number range comes into play, 0 to 1,000 ohms. Well, a closed switch or a good fuse should read a perfect 0. A healthy load, like say a motor winding, a relay coil, or a heating element, will actually have a measurable resistance. It won't be absolute 0, and it certainly won't be infinity. It usually falls somewhere in the 0 to 1,000 ohms range. It's not a roadblock, and it's not a free highway. It's more like a toll booth, making those electrons do some actual work. Moving right along to Section 2, the golden rules of testing. Okay, this is your absolutely mandatory isolation sequence when testing for resistance. Step 1, de-energize the circuit using proper lockout-tagout procedures. Step 2, perform a live-dead live voltage test to definitively prove it's dead. And Step 3, isolate the component. Remember, an ohmmeter actually uses its own internal battery to push a tiny voltage and measure resistance. If you put your meter on a live, energized circuit, that external power will absolutely destroy your meter. And worse, it could cause a highly dangerous arc flash. Now, I really need to highlight a crucial warning here. Just flipping a switch off, that is never proof that a circuit is safe. A basic switch might only break one leg of power, leaving the rest of the unit dangerously live and energized to ground. You've got to always verify a true 0 energy state with a properly rated contact meter before you ever switch your dial over to ohms. Which brings us to Section 3, loads, good, open, or shorted. Take a close look at how this brilliantly illustrates the physical difference between our readings. On the top left, a dead short across closed contacts reads exactly 0 ohms. On the bottom right, an open contact reads infinity, or OL. But look closely at the top right. A healthy coil is showing actual measurable resistance on the needle. It's doing its job. It's slowing the electrons down to convert that electrical energy into a magnetic field, but it is not stopping them completely. So honestly, use this matrix as your bulletproof decoder ring for basically any load you test out in the field. A good load has an intact winding and shows measurable ohms, say 20 or 50 or 200 ohms. An open load has a physically broken wire inside, so the meter reads OL. And a shorted load? That means the internal winding has literally melted together or completely bypassed its path, giving you a 0 ohm reading when you really should be seeing measurable resistance. All right, Section 4. Testing switches and breakers. So switches are placed in series with a load, right? They're kind of the traffic cops controlling the current. They come in 2 primary flavors, normally open and normally closed. But here's the trick that catches a lot of people. Normal just describes the reference state of the switch when the system is completely de-energized. Like, imagine it's just sitting on a shelf in a cardboard box, doing absolutely nothing. It has absolutely nothing to do with whether the system is operating normally out in the field. I absolutely love this habit from the source material. State the component's position out loud before you test it. Before you even apply your meter probes, actually declare what the switch should be doing. Like, hey, this pressure switch should be closed right now because there's pressure. If you don't declare what the reading is supposed to be beforehand, how are you going to know if your meter's reading is actually indicating a fault? Let's contrast these states directly. A healthy switch or breaker, well, it should act just like a solid wire when it's closed, giving you 0 ohms. And when it opens, it should act like a totally broken bridge, reading OL. Simple as that. A faulty switch, however, might actually show a measurable resistance, like 15 or 40 ohms, when it's supposed to be closed. And that indicates pitted, dirty, or burned contacts. Or, on the flip side, it might read 0 ohms when it's supposed to be open, meaning the contacts have literally welded themselves shut. Yikes. And finally, Section 5, Evaluating Protection Fuses. Think of fuses as the bodyguards of the system. They are one-time overcurrent devices. If they blow, hey, they did their ultimate job to protect the conductors and the equipment. But we've got to remember those isolation rules. When you're testing a fuse for continuity, it must be completely removed from the block, or at the very least, heavily isolated. If you just leave it wired in, parallel paths in the circuit can feed back right through your meter and give you a false 0 ohm reading. That'll completely trick you into thinking a blown fuse is perfectly fine. Now, if you measure a fuse, it reads OL, and you know for sure it's blown, you've got to follow some pretty strict rules for replacing it. You have to match the voltage rating, the ampere rating, the interrupting rating, and the time characteristic. Is it a fast blow or a time delay fuse? But here is the single most important takeaway of this entire section. A blown fuse is just a symptom. Replacing a blown fuse without finding the actual short circuit or overload that caused it, that's literally just reloading the weapon. It's gonna blow right again. To tie this whole thing together, here is your ultimate diagnostic cheat sheet. I highly recommend taking a mental snapshot of this matrix for your next field call. For a switch, 0 ohms is closed, OL is open. For a load, you want measurable ohms between 0 and 1000. 0 is a dead short, OL is open. And for a fuse, 0 ohms is a good, intact fuse, and OL means it's blown. If you can master this matrix, you will completely master your meter. Which brings us to a final, kind of provocative question to chew on. Let's say you properly isolated the circuit, you measured OL across a fuse, correctly identified it as blown, and swapped it out with the perfect replacement. Awesome. But did you actually find the true physical cause of that overcurrent, or did you just reset a ticking time bomb? Next time you grab your multimeter, remember to look past the digital numbers on the screen and really visualize that physical path of the electrons. Thanks so much for joining us on this explainer, and hey, keep decoding.